So that's like right.
I was trying to talk to him, he's teaching. He's taught something.
That's what that was on me.
Yeah, no, it wasn't too bad. Did you go to the recitation session?
I looked.
All right, Cody, can you hear me?
Yeah, I can hear you. Can you hear me?
Yep, good.
Perfect.
So one person online today, okay. And everybody else is in class, am I correct? Oh, we still have time. Continue chatting, although it's captured because recording automatically starts. Go ahead, yeah.
I was waiting to the
Do
camera.
you want a camera? Do you want Yeah, go ahead.
Question for you.
Question,
So
yeah.
the book that's not required, the textbook that's not required for this class, but is recommended.
Textbook, okay, yeah, I recommend you two books. It's not really textbook, in my opinion. In other words, if you are aero person,
Right,
of course you have those two books, kind of books.
yeah,
One is Anderson's Introduction to Flight. Everybody has that book, right? Quite frankly. The other one is Introduction, Fundamentals of Aerodynamics, Anderson.
okay,
Those two are basically, well, you're not going to lose anything if you buy it. It could be like older version. Any version is fine, any edition is fine, but I think you should have it.
okay,
Everything we cover in class is based on those two books, Anderson,
okay,
and which is probably fairly uniform across this country,
Yeah.
as long as aerodynamics is concerned. Actually, I was educated by Barton Smith's Aerodynamics, which is Air Force, coming from Air Force. Now, Anderson is from academia,
okay.
University of Maryland, so it's a slightly different kind of area. So it seems like everything is from coming from Air Force side or academia side.
Yeah.
Anderson, Max Reda, everybody knows those people.
Okay,
Yeah,
so where should we be in the textbook at this point?
I don't know. I picked up, cherry picked all of those contents. I kind of rearranged everything
Okay,
in a way that it really makes sense to me. So I don't know where is the origin of this content.
okay, but just to have it. in-
But you can find it. You can
Yeah.
find the contents of today's lecture in either Anderson's Intro to Flight or Fundamentals of Aerodynamics.
Okay, and then you can read it in just one.
You
spot.
can read it, yeah, sure. Suppose if you cannot read it, if you cannot sleep at night,
Yeah,
go ahead, grab Introduction to Flight, try to read it in your bed. Before you know it, you're gonna drop your book on your face. What's going on? You fell asleep. I used to be doing that. Oh man, I can't sleep tonight. Let's read Introduction to Flight of Anderson. Actually, it's a great book. So actually, you cannot even sleep because it's
I
so
was
interesting.
just getting that, yeah.
Yeah, it's a nice book. Fun to read. Okay, yeah, let's do one more minute. So I took my mask off because I received a complaint from Dean of Engineering. He said, "Oh, you shouldn't be wearing your mask." What should I do? Well, don't you have a face mask? Oh yeah, I have a face mask. Strange. Not a face mask, a face shield. So, what time is it? Oh, 1 o'clock. Let me just close the door. All right. So, okay. So today, one person online. So suppose Cody, if I forget to share my desktop, that means you keep watching everybody's face throughout the class time. So please tell me, because this actually happened to EGR 115 class. 3 students online. I forgot to share my desktop throughout like hour and a half class. They didn't complain to me. They just kept watching. In this case, I can see Dylan, Robert. I mean, those faces all the time for hour and a half, and they didn't complain. I couldn't believe it.
Thank you.
Come on in. Not too late. I haven't taken attendance yet, so let's just take attendance now. And then before I forget, okay, let me just share my desktop, because I usually forget about Okay, so now I'm showing my desktop right now. Okay. That's right. So let's just be ready to take in-class attendance, everybody. I hope you have your piece of paper, avatar paper. Okay. All right. So yeah, that, there are, oh, cool. I write. Robert, I write. Heidi, Hunter, Jason, Ismail, Jaden, Michael, so Ian, Tika, Anthony, Richard, and
I'm just like this is electrical engineering minus right here.
So airport, I would see people, you have something to
I think that would make it.
have it, we're on.
I think that would make it double E paper.
I probably make any seeing that.
Yep, we're done. Let me go check. Okay. So attendance, then I saw somebody walked out. I don't know what's going on. Did I? Am I the only one? I saw somebody walked out.
I think they want to open the door.
Okay, that's it. Do you wanna open the door? I can do that. If you prefer that. In other words, circulation ventilation more important. So I can do that.
Are the pressure circulating outside?
I mean, it's fine. It's
Alleviate
Because I want to do the best practice, I don't want to waste your health. Okay. So I'm not wearing mask. I hope it is okay for you. I'm still wearing face shield. If you want me to wear a mask, I'm going to do that. I have masks. So please feel free to tell me what is the best practice to protect you, because your health is #1 concern to me. Okay. So if you want me to wear a mask, I can. Do you want to? No.
No, it's a lot easier to hear.
All right. So I think this is much more clear to hear than just to wear a mask and I have to yell at you all the time. Okay. So today, let's just to take a look at updates. There's no new update since Monday. Today's Wednesday, so I hope you're working on something. Oh, actually, didn't you turn in something? Whoa, I keep forgetting it. Oh my goodness. Today is like what? You submitted quiz 2 already? I forgot to take it. I'm sorry. Damn it, I keep doing that. So file folder is still up. Because I completely forgot to take it before noon, because usually I cook like my sandwich and I completely forget about taking files away. I have to probably break my habit. But, sorry, I forgot to take it. Still up. So, I don't know. I apologize. I try to make sure I take your file starting from Friday. I promise. I'm so sorry. I feel terrible about it, not taking your file.
It's okay, we forgive you.
Okay, thank you.
We forgive you.
Okay. Thank you very much. I appreciate
You're
it.
fine.
You can always take advantage of that last minute. Oh, Dr. H is forgetting this. Continue working. Okay, anyways, so Friday is coming up. So how was your quiz 2, by the way?
It was.
Well, as long as you figured out quiz 0 problem 2, it's just a higher altitude. That means you have to go through a 2-stage process.
Yeah.
Gradient, isothermal, what's the ratio?
Right.
Right? That's what it is. Yeah.
The first part.
Quiz 0,
The first part was weird.
quiz
Yeah,
0
'cause-
oh, that's right.
The first part, because you said
Huh?
don't use a hypostatic equation.
Hydrostatic equation.
It's
So
a-
first part comes up with like, what the hell is negative?
Negative pressure.
Yeah.
Yeah.
What do you mean? Well, that means assumption is all wrong for that high altitude. You cannot use that kind of equation. to predict the pressure in higher altitude. Hydrostatic pressure fails. Because why? Density can never be constant in that high altitude. Now you run something, and then you realize it. Okay, good. That's the whole point. So quiz 3 is coming up before you know it. So hopefully you continue working on quiz 0 problem 3. So can you guess what's going to be the quiz 3?
Problem 4 from quiz 0.
Problem 3 of quiz 0 was, what is it?
It's about pressure.
Pressure
To
within wind tunnel, right? Wind tunnel. Wind tunnel, yes. What is the governing idea of wind tunnel? What is the basis or equation? You have to pick it up to predict the wind tunnel airspeed. Bernoulli's equation, here we go. So low speed wind tunnel is, of course, it's low speed. You can still use Bernoulli's equation to predict the pressure and velocity within the wind tunnel. We're going to do that. That's next to come. So today's subject is, of course, something to do with that. Remember in last class we talked about, by the way, you know, since I'm looking at my lecture video all the time, I realized, wait a second, this is not Reynolds, this is E. Sorry about that. Reynolds.
Okay, yeah.
Misspelled, sorry about that. Yeah, so I'm correcting it officially in today's video. Reynolds transport theorem. So this is fundamentals of fluid mechanics. Essentially, 80% or more of the fluid mechanics is coming from Reynolds transport. Now we looked at conservation mass in last class. Now today we are going to take a look at conservation of linear momentum. What is that? Conservation of linear momentum. In a nutshell, that's Newton's second law of motion. Newton's second law of motion is the single thing you're going to learn from dynamics class. So you took dynamics, you learned only one thing. F equals to ma, that's it. Okay? So we're going to revisit that today. F equals to ma, that's Newton's second law of motion. Okay? So let's just go down to page, before we move on, let's take a look at page 3. Okay? Because page 3, here is an example problem. Page 3. Page 3. Okay. Consider a convergent circular duct with an inlet diameter 10 meters. Wow, that's huge. It could be rocket nozzle or something. Air enters this duct with a velocity 20 meters per second and leaves the duct to exit with a velocity 25 meters per second. What is the area of the duct exit? Oh, okay. So of course you're going to apply continuity to find out. Of course, I'm going to apply A1 B1 is equal to A2 B2. Jump right into here, right? Then you feel like, oh, wait a minute. Are you sure you're going to do that? I feel very weird. I don't want to do that. But since Dr. H is doing it, just to stay, you know, sit back and watch, okay? Oh, you know, this is continuity. So this actually gives you, oh, A2 is equal to A1 over. Some of you actually stopped taking notes. I agree. This could be a piece of crap. Oh, okay. So this is cross section of A1 is given, right? Pi over 4 times diameter 10 meters squared. Okay. Yeah. This is the cross section area A1 inlet. Velocity V1 is 20 meters per second. Velocity V2 25 meters per second. Okay. Or if you punch the number, you get 62.832 meters squared. I'm done. Homework done. You think so? Do you think so? Do you think this could happen for your homework?
If we were dreaming.
If you're dreaming, yeah, that's right. So before you casually do such a number, you know, plug and check kind of thing, you have to think twice. Am I doing right thing? What is the number one thing you have to think about?
Compressibility.
Compressibility. Okay, that's right. Is this incompressible flow? How can you tell that kind of stuff?
Density. Well, Reynolds number.
Reynolds number. Reynolds number?
Not Reynolds number. Mach.
Mach number.
Yeah.
There we go.
Yeah, that's the one.
That's right. Mach number. So lots of things to double check. Mach number, oh, I shouldn't use that. Mach number requires important information. What is it? Mach number of inlet, Mach number of outlet. If you want to find out that kind of stuff, you need to keep asking, hey, I need the extra information. What are those? You don't have to raise your hand. Go ahead.
You need the speed of sound.
Speed of sound. What is speed of sound? That's right. That's correct. Speed of sound. It says speed of sound is A.
Okay.
Maybe C for fluid mechanics, but
Yes.
A. Yeah. What is speed of sound equation? Go ahead. Go ahead.
Square root of gamma r.
Square root
Square root of gamma r g c t.
gamma RT. Gamma is
Where GC
1.4 for air. So this is usually called gamma. Gamma is oftentimes used specific weight in fluid mechanics, so it's kind of confusing. But this gamma is a ratio of a specific heat. Specific heat ratio Cp over Cv is gamma. Okay, we're gonna cover that later, a little bit later. We're gonna cover that. So this is gamma, specific heat ratio. If it's a standard air, it's 1.4. R is of course gas constant. You know that value, 287 or 1716. T is what? Temperature. So now you need to realize speed of sound is something you need to know. In order to find out speed of sound, you need to know the temperature. So you need to be given index temperature, T1. You need to be given outlet temperature, T2, in order to figure out the Mach number of each inlet and outlet. Okay? So you need to continue discussion about this problem. Hey, wait a minute, before casually pick up this equation, use it, we have to continue. Okay, so first of all, what is the Mach number? Well, I don't know. What is the temperature of inlet? What is the temperature of outlet? You need to give me that, because this is going to give me, at least assuming ideal gas, it's going to give me speed of sound. And then based off of the sea level temperature, if this is sea level, speed of sound, I can tell, is in terms of meter per second, is about 310 or 20-ish. So let's say if you pick up a calculator, divide 20 divided by 320, what is the Mach number? Is it more or less than 0.3? Very less than 0.3, right? Because it's 20 meters per second. If it's sea level, Mach number is 0.0 something. How about 25 meters per second? Well, yeah, it's really low. So yeah, this is both inlet and outlet, less than 0.3 incompressible subsonic if it's sea level, assuming.
Right.
Then, okay, so now we can assume density constant. And then, is this a steady flow, by the way?
Yeah.
Yeah, I think so, looks like. Because it's not a rocket nozzle, you're just burning a gas inside and then accelerating kind of stuff. No, it's not. It's just air in, air out. Steady state. Let's assume that way. If so, you can do this. Lots of things are assumed, and then we're not going to bypass those assumptions from now on. Go ahead.
So if we were given this on like a quiz,
Yeah.
would we say, okay, I assume that it's at sea level, therefore I also assume that it's at steady state, and then go ahead and solve?
I guess so. Or program may specifically say those things.
Okay.
Yeah.
Okay.
Right.
It's not something where you would be like, I can't solve it because I don't have these materials, and then
You can actually complain like that in quiz or exam.
Okay.
Oh, Dr. H, you didn't give me this condition. I refuse to solve this exam problem. How is that kind of thing? Then continue arguing after the exam. You can try. Whoa, oh man, it's scary, but you can do it as a student. Go ahead.
Because there's a divergent duct and then a convergent duct. But you only
Yeah, okay. Well, this is what? You've got 62 meters square, so diameter-wise, you are 25, you're accelerating. That means if the velocity goes up, it's convergent duct. So you're talking about this stuff. Because it's raw speed, you have 20 meters per second comes in, accelerated to 25. This is most likely convergent duct. So from that. So I should probably move everything for you.
Oh, I see.
Sorry about that. Yeah, go ahead.
So if we were given this problem, you want us to go through all the steps, making sure that we can use A1, B1 is equal to.
Yeah, you have to discuss those things. In other words, ideally speaking, you have to get this equation, starting all the way from governing continuity equation, which we covered in last class. Ideally speaking, you have to start from here. You start from here. This is a converging duct. So it's a stream tube. Let's assume that way. One in, one out. It's a steady flow. And then you get this equation. Now this is the case that the density is constant. You drop it down to density, and then you get this equation. Now you are using this equation. So this whole process need to be discussed here rather than just to jump right in, plug and check. Go ahead.
In lecture 2, in some of the lecture problems, you just use the ratio, like the equations you already.
Which lecture from?
The one you want
Which
us to
one?
watch.
Which one?
A2.
Which one? Okay. Which one?
The A2 lecture.
Okay. A-2.
A-2 lecture.
A-2 lecture.
Yeah.
The one for that one YouTube only.
The YouTube lecture.
YouTube lecture. YouTube lecture A-2.
Yeah.
And then, okay. So you're talking about all of stuff A2?
Yeah.
Okay, I'm not following you, but A2, yeah, let's just take a look. Is this your complaint?
Huh?
Is this your complaint or question?
Question.
Question, okay, let's just take a look at A2. So you want to get into A2?
Yeah.
Okay, which problem?
I mean, for some of the lectures,
Which one? Not the sum of the lectures, which one I'm asking?
first problem.
First problem, let's take a look. First problem, what, this?
I think so.
Yeah.
For that one, I think you just used the pressure ratio
This.
you derived from.
This.
You didn't complete the whole
Well, I
derivation.
derived it.
Yes, yes.
And here.
I'm just saying when you do the problem.
Well, I derived it here, so you can look up the derivation process here. So simply this example problem, I picked up the equation I derived here,
Mhm.
then I used it. So
Okay.
this is plug and check problem, of course, yeah.
Okay, but.
Because
you
the
know-
equation has been derived clearly in the previous pages.
Okay,
Now, if this, so your question is, if this is given as an exam, do I have to go through the derivation? Yes or no? It depends.
okay,
If the problem is specifically asking you, hey, derive this equation, start from here, you have to do that.
Yeah.
Of course. If the problem says, hey, this is the equation given for gradient region, what is the pressure? You can pick up and plug the number, get the value out. It depends on the type of the problem. You have to be very careful about that.
same goes for homework and quizzes.
Of course, it depends on each problem. If the homework asks you to derive it, you have to derive it. If the homework is asking you, okay, what's the value, then you can pick up the equation appropriately, saying, okay, in the notes in page such and such, we derived this equation based off of that. Condition is density constant, so I can use this equation, then it's just to plug the number, get the number out. That's what we can do. That's what we are doing here. Okay. Question, go ahead.
Going back to checking the Mach number for the ducts.
Yeah, okay. Yeah.
Is it enough to just check the?
Check the.
Check the speed where it enters the duct and check the speed where it exits the duct?
That's right, both sides. So
Is that enough?
this is.
Or say if you had like a really weirdly fixed duct and the cross section was continuously changing.
That's most likely the case that it is unsteady flow. In other words, within the control volume, we are going to set the control volume for this case, right? This is a control volume. Now, within the control volume, if you have like weird things happening, like you're combusting something, really heat it up in certain section, that's, well, we cannot simplify a problem like this. You have to go through like a segment by segment, like a combustion chamber, how much energy is injected, kind of thing. Mach number may accelerate to more than 0.3, unsteady, mass is added, chemical reactions going on. You, like I said, you can always make things more complicated easily. I think I said this thing before. Yeah, it's easy to make things complicated always in engineering problems. So, but start always from simplest possible assumptions, right? In this case, okay. So again, this could be okay, 10 out of 10. This could be like a 2 out of 10 or 0 out of 10, depending on the problem. Okay. So this is basically just a simple question, right? What is the area computed? Oh, I computed. So this could be 10 out of 10, but this is not fluid mechanics. I'm not going to give you this kind of problem anyways. So you have to be ready for it. That's what I'm saying. Okay. So let's actually just take a look at, okay, course homepage once again. Homework A301. You're supposed to be working on because I'm done homework A301. Right? No, class example A301, sorry. Class example A301 is done. So you're supposed to be start working on homework A301.
Yes.
Sorry. Like, we haven't even turned to A2.
Then you go like, oh my goodness. Oh yeah. So take a look. So consider the same deck to discuss in class with an inlet diameter, blah, blah, blah. Yeah, here we go. So now I give you A2 because we solved it. Here we go. So 70 kilometer per hour gets in. What is the speed that takes? Oh, okay. I don't know. Can you find it? I don't know. Air enters this deck with a velocity 700 kilometers per hour. Oh, 700. That's pretty fast. What is the exact kilometer per hour? You have to think about it. A1, B1 equal to A2, B2. Do you think it applies for both cases? I'm not sure. You can go for it if you want to try.
Definitely not case B.
Definitely not the same kind of problem that you saw today in class. You have to think about it. Okay, what kind of extra information you needed? Is that extra information given already in the program statement? If not, you may ask that kind of thing for me. I may respond you back and you go like, oh, now I got it. I can solve this. Dr. H, you are, I don't know, you are kind of sneaky. That's what you need to be doing. Don't wait until last minute before I announce homework of unit A3 is due such and such a day. That's too late. You need to keep it up. Okay, this is the second time saying the same thing. This is error class. Keep it up, or you will be left behind. Let's move on. There's one way to slow me down. Do you know what it is? Asking questions. It's going to slow me down in class. If you stay quiet, I'm going to cover more. You have tons of things piled up. If you want to avoid it, let's heat up the discussion in class. No problem for me. I actually do enjoy discussions. Even complaints. If you have a complaint, bring it in. Let's discuss about complaint. Oh, is this complaint? Oh yeah, that's just a complaint to a Dr. H. Oh, I think he's wrong, man. Go ahead, try. Oh, I don't think you're right. Because Dr. Richard Felton, I think he said this. Then I said, oh yeah, I was wrong. I'm sorry. I have to talk to him. Sorry about that. Oops, I shouldn't continue. This is recorded. So today, okay, we are going to go back to Reynolds transport theorem once again. So we are going to take a look at the conservation of linear momentum. So do you remember the momentum equation from fluid mechanics? The governing equation that your professor gave you in fluid mechanics. This is called governing equation of linear momentum. Something called momentum equation, the integration form. Okay. You're looking at the momentum equation. This is a fluid mechanics version. Like I said, Iowa State University, Manson, Young, and Okishi. This is John D. Anderson's same equation of linear momentum, University of Maryland, textbook of fundamentals of aerodynamics. It's the same exact equation, slightly different format. Now, aerodynamics version has more specifically 3 different kinds of force is listed. Okay, so this is summation of all external force contents added together is going to balance up with 2 things. One is unsteady change of linear momentum within the control volume. This is a momentum flow across the control surface. Those 2 added together is going to be summation of all external forces added to. So in aerodynamics, some of the force components will never happen. Fluid mechanics, it will. But the aerodynamics, some of the force components we can ignore. So three specific type of forces we are going to consider. One is a force due to pressure. This is it. So force is created due to the pressure difference. This is a high pressure zone, this is a low pressure zone. Because of that pressure difference, you create the force in this direction. This is airplane's wing. You create high pressure zone, low pressure zone. As a result, force is created in this direction. What do you call that? It's lift. Okay? So force due to pressure difference. That's one thing we consider. Number two, something called a body force. Listen. What is that? Typically meaning it's a gravity. Weight of yourself in aerodynamics. Now, if you're looking at the flow field of air, do you care about how heavy your air particle really is? Okay, stretch out your hand. Do you feel today's air is kind of heavy? No. You basically, naturally speaking, you ignore the gravity, right? But in fluid mechanics, you can't. Why is that? Here's my victory. Go ahead, grab it. Oh man, this is heavy. Of course. This is your air. Oh, I don't feel anything. So that's the difference. So body forces, typically in air, we oftentimes ignore this. That's called no body force assumption. Because it's air. Usually, okay. So third type of force, it's called viscous force, okay? Do you know the viscosity creates the boundary layer on the surface of a body, okay? Now air, of course, comes with the viscosity, even if it's lower than liquid typically. So when the airplane wing is moving forward, of course, on the surface, because of the air viscosity, the air is going to stick on the surface, creating very thin boundary layer within. And then tau is equal to mu dV dy. Mu is the viscosity. The tau is the shear stress. Now, so shear stress is developed over the thin surface of your wing cross section, okay, wing over the surface. That is going to create the drag of airplane. It's called parasite drag or skin friction drag, something like that. That is a viscous force. Okay. Now, oftentimes, at least in Aero 1, not the Aero 2 though, we can ignore this. In other words, we purposefully avoid the discussion of the boundary layer very close by surface because it's so thin. Oftentimes in low speed and high speed, we can ignore, especially high speed, we can ignore that. High speed compressibility kicks in more than viscosity. So high speed airplane, oftentimes we completely ignore the viscosity. Low speed, yeah, we have to include sometimes. But oftentimes we choose to ignore even though might not be very bad, sometimes very bad, practice to ignore such a thing. But sometimes we ignore it. This is called invasive, okay? In other words, completely ignore the boundary layer. Viscosity mu is 0. Okay? So that is this force. So 3 different kind of forces we are going to deal with. Out of those 3, 2 of them is oftentimes ignored. And then we start with that simplification in Aero 1. What kind of equation you can expect from those assumptions? If the flow is completely steady, of course, this component goes away. This is unsteady component. If the flow is steady, this component drops off completely. It actually leaving only 2 things. One is momentum flow in, flow out, and then force due to pressure difference. Those 2 need to be in balance. Have you ever seen an equation comes from that concept in fluid mechanics? This is your real skill. Expect that whenever the question casted to the class and everybody stays silent, that is the question, at the job interview, people ask you, well, I said the question saying, okay, based on the concept that flow is a steady state, I choose to ignore the body force, and then it's implicit. Then you can come up with an important equation. You can use it in fluid mechanics. What is that equation? Not Tabernodes, but very close. Euler's equation. Let's just take a look. Unit C of my fluid mechanics notes. This is now moving fluid. Now we are talking about fluid in motion. Now, do you remember steady flow that actually defines the streamlines in the flow field, right?
Right.
Correct. In other words, streamlines are the lines drawn in the flow field that the direction is always tangent to the local velocity vector. So suppose if you draw one streamline, you can use that streamline as a coordinate system, something called streamline coordinate system. Do you know what I'm talking about? This is an important concept in fluid mechanics. Very important concept in fluid mechanics. This is going to set the foundation of aerodynamics of use of streamlines. This is a streamline coordinate S. Have you ever seen this S? Of course you've seen it. I know it. So if you think about acceleration of this particle along this streamline, in a direction S is the direction tangent to the streamline. This is the acceleration of this small tiny particle. You have two components of this acceleration. All of a sudden, this seems like a dynamics class, but acceleration in direction tangent, acceleration in direction normal to the path. One is called tangential acceleration, AS. The other one is called AN. What's this? Normal acceleration, or in other words, in dynamics, this is called centripetal acceleration. Do you remember those?
Yeah.
Okay, so this is a normal acceleration. This is a centripetal acceleration. Two things happen. So we are going to purposefully pick up only this one. Normal direction acceleration, AS. Okay, this thing. Have you ever seen this? This is acceleration in a direction tangent to the path called the streamline. Okay? Yeah. And then, I believe you did in fluid mechanics. If you put your eye on a single particle, which is moving along this streamline, let's just apply equation of motion. What the heck is that? Equation of motion. F equal to ma. Let's apply F equal to ma, equation of motion, in two directions. One is direction tangent to the path, to the streamline. Direction perpendicular to the path, to the streamline. You come up with two equations. What are those? Euler's equation. That's what you did. Okay. This is Euler's equation. Have you ever seen this? Of course you've seen it. I'm not going to take your comment. Oh, I've never seen it. My teacher didn't cover. Oh, give me a break. I don't believe that. If so, you've been probably sleeping in your class. Everybody should cover this. So anyways, so this is a fluid mechanics version of Euler's equation. Something is different from aero. What is different? If you apply this equation to aerodynamics, you can simplify one thing. What is it? Go ahead.
Can you just discuss that it's the normal direction force?
Yeah, no. This is the force in tangential direction, so it's S direction. If you apply the F equal to ma in this direction, you have another Euler's equation. Let me show you. Yeah. Just a minute. Yeah, this is another Euler's equation, direction normal to the path. Now, in this case, this thing shows up. This is called centripetal, or in the fluid mechanics, this is called centrifugal acceleration. Do you remember those things? Centrifugal acceleration, centrifugal compressor. That is the mechanism of centrifugal compressor to compress and make it high pressure. Okay, do not miss any of those basic, very important concepts. Okay, so let's just go back to, okay. So this is Euler's equation. This is fluid mechanics version. You can simplify one thing. What you can simplify one thing? Of course, this is air. Who cares about this term? Gamma is 0. Gamma is specific weight. What is the weight of air? Who cares? 0. Let's assume that. So this is Euler's equation in aerodynamics. Let me just write it down. Minus dP ds is equal to rho times B dV ds. Okay. Euler's equation of aerodynamics. Today, I'm going to spend some time. Let's re-derive this equation. Question, go ahead.
Why did you say it was negative? Maybe gamma sine theta was 0?
You're going to find out in today's lecture, hopefully.
Okay.
Yeah, wait and see. So anyways, this is nothing new. It's coming from fluid mechanics. So let's just go back to aerodynamics. So today's lecture. So let's just put your eye on a single, what's this? This is air, chunk of air, maybe air particle, small, very small, tiny air, chunk of air, originally cubic element. This is a small, tiny cubic element of air moving along this path called the streamline. Okay? Now, I'm going to derive this equation based on x and y and z, 3D Cartesian coordinate, but at this instance here, happen to be the direction of velocity is in the direction of x. Okay? It just happened to be. Okay? Now, if you really zoom in this small tiny chunk of air, it looks like this. So this is a cubic element with the size of dx, dy, dz. Left-hand side, pressure is P. Now, right-hand side is a different pressure. Pressure is P plus dP dx dx. So this component comes in with a variation of a pressure in the direction of x coming from first order of Taylor series expansion, which is a differential variation of the pressure in the direction of x. It just gives you a general sense that the pressure is not a constant. It's a variable into x direction. So, like I said, this is the case that we completely ignore the body force. Gravity is 0. Viscosity, no, I'm not going to even include that viscosity. So assumption, steady, no body force, no viscosity, and then you apply F equal to ma for this body moving around this streamline. What kind of equation do you think you can get?
You might be able to get it on the right one.
Not the algebraic one. This is going to be differential equation still, but you're going to get Euler's equation. Okay, that's what you did in fluids. Let's just do it again here. So today I'm going to derive Euler's equation. Aerodynamics version. Okay, now we are going to start with assumption steady flow. Number 2 is no body force. Typically means the gravity we ignore for this small tiny body of air. Number 3, inviscid, viscosity 0. We're not going to even talk about boundary layer. Inviscid. So those 3 assumptions, okay? Now only one force you have to deal with, if so, right? What kind of force is that?
Pressure.
Pressure, okay? So force is developed because of the pressure difference. So pressure is different from left-hand side and right-hand side. Okay, left-hand side is pressure is P. Right-hand side pressure is P plus dP dx. Okay, P plus dP dx times dx. This is essentially first order assumption of Taylor series expansion. And then this is the streamline. Then happen to be you are in this position where the velocity is B, and then happen to be right here, direction X is, this is the direction X. So velocity B is, okay, let's be careful. Velocity B is velocity B magnitude in the direction X, BI. So this is the situation right here, right now. Magnitude of velocity is B. Direction is in X direction, and happen to be along the streamline. That means this is the direction of the velocity. Is happen to be an X. Okay, so that's the condition. So I'm going to apply F equal to ma for this case. It's very simple. In other words, let's apply F equal to ma in X direction. Okay. So what do you have? This pressure P multiplied by the area on this face, right? What's the area on this face? Multiplied by P. This is going to be a force due to pressure. This is what? dy dz? Something like that. Left hand side is pressure P times dy dz. That's the area of left hand side surface where pressure P is acting on. So this is a force due to pressure on your left hand side face. This is positive because it's in positive X direction. Okay, how about the other side? The other side is negative because the pressure is opposing against it, right? It's a negative X direction force P. So this is force P. This is not the force P. P plus. Right hand side face is P plus dP dx dx. Okay, that's the pressure on your right hand side face. So what is the area? What's this dy dz? I'm sorry, dy dz. So those two are the force, right? F, force due to pressure difference, must be equal to mass. What is the mass? Mass is the density times the volume, right? No. Yeah, density times the volume.
Yes.
Suppose if the density is rho, let's multiply by the volume. What is the volume of this box? Dx, dy, dz. That's right. And then, ooh, what is acceleration? Acceleration is, of course, velocity take differential with respect to t. Then you go like, wait a second. Can you do such a thing? Have you taken dynamics?
Right now.
Yeah.
Yeah. Can you do this?
No, it doesn't become separable.
dv dx is a problem. Why is that? Velocity is a function of position, which is x, and also a function of time. You have to do either partial derivative or derivative of parts. Do you know what I'm talking about?
Yeah.
Otherwise, mathematical professor will kill you. You know, you see the professor Watanabe, he's going to kill you. He's a mathematical guy. Mathematically speaking, how can you handle the velocity, which is a dependent, which is a function of two variables? Function of two variables, you have to differentiate. Go ahead.
You could rewrite it as v dv dx.
That's right. So go ahead, dv dx once, and dx dt. You have to do this, of course. Then you realize, what is dx dt? In other words, position change in x direction with respect to time. What the heck is that?
Awesome.
It's a velocity. What are you talking about? So this is velocity v. So this is equal to v dv dx. How's that? So that's what this thing is, right? So conclusion. By the way, if you take a close look at it, this is p dy dz. Oops. About 5 more minutes. P times dy dz. Let me just go over. So, okay. So, wait a minute. This whole thing and this whole thing cancels out if you take a close look at it.
Oh, yeah.
Okay, right? Then let's move on from there. You're going to be negative dp dx dx dy dz equal to density rho times dx dy dz b times dB dx. Of course, you can cancel out this whole thing. As a result, you're going to get this equation. dP is equal to negative rho b dP. What is this? What is this equation? Have you ever seen it before? This is called Euler's equation in fluid mechanics, which is very bit simplified for error. Go ahead.
Oh, never mind. I see.
So, if you cannot believe your eyes, I can show you once again Euler's equation from fluid mechanics. Is this the same equation? Yeah, because along the path S, you can simplify it, okay? Along the path S, this is called the streamline. You don't have to use S. This is negative dP is equal to rho times B dP. Here we go. This is the equation we got today. So this is Euler's equation, which is applicable only along the direction of the streamline. So you have to add along a streamline. This equation is applicable only in the direction tangent to that given streamline. Okay, so next class, okay? We're going to start from this Euler's equation, and then let's just get Bernoulli, something you want to have. Now you can solve something. So let's stop here today. Do you have any question? Go ahead.
So the equation we got up above, the momentum equation, that looks a lot like Euler's equation. Is that just-
Well, yeah, momentum equation is, if you take a close look at it, if it's steady state, this term drops off, and then those two terms drops off with the assumption of no body force in implicit. And those two imbalance, that is essentially Euler's equation. Yeah, there we go. You're right. Any other question? Have a good day. And then we're going to see you back on Friday. Continue working on your quiz zero. All right, people online, do you have a question? I'm going to stop recording.